Hey everyone, how are you? I just finished lunch, sort of. The countdown is really scary when you're trying to finish lunch as fast as you can and class is starting. But good to see everyone again. All right. So today we're just going to continue talking about graphs. We're in the world of graphs now. Still finishing lunch. Great. So last time we were talking about some trees, right? So last time we were talking about some trees. And what I want to focus on is to talk about these different ways that you could think of a tree. One of them was when we just thought of drawing a tree where you take a vertex, you add some stuff. Oh, sorry. Oh, no worries, don't worry. So you take a tree, you start with a vertex, you just kind of keep adding on edge and vertex. So if you can see, I'm just kind of drawing something out where every time I just keep adding an edge and a vertex. And I could think of a definition of something called a tree growing procedure. Tree growing procedure. And what that is you start with one vertex and you just keep adding on a vertex and an edge over and over again. Then you keep adding. Just a second. Something here seems to have temporarily stopped. Looks like it's fine. Okay. Yeah. So you just keep doing this over and over again, and that makes a tree. That looks like a tree. There's this joke that in computer science, you often see the trees doing this, right? And so these are these trees that go downwards, and so on. And this could be an example of a tree. And there's some joke which says that the trees go upside down because the computer scientists never went outside and saw a real tree. But anyway, that was a joke in one of the books that we used to use for this class. But anyway, so these are the trees. But we also saw, I think in the last class, that some people made some observation that, these trees here, there's no cycles. And they're also connected in some sense. So there's another definition. In fact, this thing was the tree growing procedure. But what you'll often see if you look at any graph theory textbook is it says that a tree is equal to a connected acyclic graph. Okay, so now we need to kind of dig into these words because I want to now show these two things are the same. Of course, you're only allowed to define something once in math. You can't say a tree is this, that's a definition. And another definition is a tree is also this. No, only one of those can be a definition, and the other one has to be a theorem, where you need to prove that they're actually the same thing. Okay, so in that case, before I go on, I need to discuss what each of these words means. So the connected just means that from any vertex you can get to any other vertex just by walking along some edges. So connected means you can go from any vertex to any other. I'll just leave it that way. You can go from any vertex to any other. Strictly speaking, it's on a finite path. Now, we aren't even going to talk about infinite trees in this class. So just think of everything as finite. And acyclic is what you'd expect it to mean. A means not. So acyclic means no cycles. And if you remember from last time, a cycle means that you go from a vertex to another vertex to another vertex, and eventually you get back to the same vertex. Cycle actually means you use different vertices every time and different edges every time. However, if you have no cycles of that kind, where cycle is very restrictive. You're not even allowed to repeat an edge, or even repeat a vertex. And if there's none of those cycles, there's definitely no cycles that do repeat edges, because if there was one that repeated edges, there's one that doesn't repeat edges. So acyclic is the correct thing. It's just you just can't go in a loop. Okay, so now we want to go and prove these two are the same. So the theorem is that actually the set of all the trees which are connected acyclic graphs is the same as the set of all things you can get from the tree growing procedure. And this is the first theorem in graph theory that I often teach. where we have to go and actually prove something. The theorem is that the set of all finite graphs that are connected and acyclic is equal to the set of all finite graphs you can get from the tree growing procedure. Okay, and that's actually quite interesting, because if somebody just told you, I want to talk about trees, and you say, yeah, those are the ones where you just keep adding vertex and edge, that's really cumbersome. And is there an easy way to check whether or not something is a tree? The interesting thing is the first definition gives you a very easy way to make trees. You just kind of make it, you grow it. But if you want to check whether something is a tree, somehow the second one is maybe a little bit easier. It's like just make sure that from every vertex to every other vertex you can get there, and somehow make sure that you have no cycles. Although these are all equivalent, because in some sense you could just show that you can grow the tree. But let's show that these two are the same. If I need to show they're the same, what I need to say is, when you prove two sets are equal, you show that everything in one set is also in another one, and then you show that everything in the other set was also in the first. Which of these is easier? What do you think? Do you think it's easier to show that everything you can make from the tree growing procedure is connected and acyclic? Or do you think it's easier to show that everything which is somehow connected and acyclic can be made by the tree growing procedure? Jack?
Because my first thought is that, at least starting with the tree growing procedure, it's pretty clear to me why it's connected. Not so much about the acyclic part, but
Yeah.
so I'm suggesting that direction.
Good. So I'm going to do this way. Oops, it goes the other way. I'm going to write this containment first. Right? I'm trying to show equals. I'm trying to show these two sets are the same. So the first thing we're going to do is we're going to show why is it that everything you get from the tree growing procedure is both connected and acyclic. Okay? So how would you do this? Well, now you get to start with anything from the tree growing procedure. And what you're saying is it's clearly connected. I'll actually give you that clearly. Honestly, is the connected doesn't just mean that everything is connected to the thing you start from. Connected means that anything can get to anything else. But the reason why it's connected is because if everything is connected to the root, the thing that you start from, well then you can always go to that root and then go to the other one. Does that make sense? If I had to walk from one vertex to the other, I know that each of them has some path all the way down to the root. And wherever they first touch, those paths first touch, yeah, short circuit, it's okay. But in my definition of connected, I just said you can get from one to the other. It doesn't have to be a super efficient way of getting. Just kind of go and then go. So I'm just going to give that clearly. And maybe just put a little parentheses. Any two vertices can go via the root. Root was this first vertex that got created in this tree growing procedure. Well, the second part is acyclic. How would you show that if you're just going to grow something by add on a vertex, add on an edge, add on a vertex, add on an edge, how do you know that you'll never have a cycle? Ah, Andrew.
You have to add a vertex and an edge together, and in order to have a cycle, you have to add just an edge.
Oh, okay. So good. So the next one is like, that's the one where we have to think a little bit. I'm going to use the next screen so I have more space, right? So we are still on the contains side, which is this like containing that way, okay? And remains to show if you're from the tree growing procedure, then no cycles. And your thought was somehow, it's because how do you make a cycle? You've got to put the last thing in somehow. You're saying somehow you're adding a vertex and an edge, adding a vertex and an edge all the time. but it's always a new vertex. So the intuition is you're always adding a new vertex and edge. So you never get around to closing the cycle. Okay, so that's right on the level of intuition. If you're curious what it might look like to give like a rigorous proof of this, honestly, this is okay enough for me. It's like, yeah, it seems right. But I want to show you how, if you wanted to really say, but does that really mean you'll never close the cycle? Here's a way to think of it. Always, like, if you do proof by contradiction, that's the easiest way. If you're trying to show there's no cycles, then you say, okay, I got a cycle. I want to stare at it. Once you can stare at a cycle, you can try to find a contradiction. And here's how to make it rigorous. Well, assume there's a cycle. Assume there's a cycle. Okay? And then now the thing about this cycle is, let's go and think about which of those vertices is the last one to be placed in that cycle. Because we're sort of thinking about how you might be able to put that last edge in. I want to just like make that thing rigorous. So it's like, it's a cycle, it's got vertices in it, and at some point you get to put the last vertex into the cycle, because the tree growing procedure is adding vertex, adding edge, adding vertex, adding edge. So focus on the moment when the last vertex of that cycle was grown. I'm calling it grown because we have a tree growing procedure. So at some point the last vertex comes in. Last vertex. Last vertex is the pink thing. That's the last. Well, when it came in with an edge. But there's the rest of the cycle too. Oops. So there's the rest of the cycle. I'm just going to draw the cycle. Here's the rest of the cycle. There's a cycle somehow. We're claiming there's a cycle that gets grown somehow. And the important thing about these edges, which I'm drawing here, is that these edges might already be there, or they might not. These edges may or may not already be here, be in the graph when that last vertex of the cycle grew. But of course, we're going to study this more carefully. So can anyone give me some ideas of how I could turn this rigorous? I want a straight up contradiction that says, no, there's no way I can ever, by the end, get all of those edges in. I want to say, that's my last vertex I added. How do I get a contradiction? Ooh, Andres.
So the tree growing process starts with just one vertex, and then after that we add edges and vertices. So that means we'll always have one less edge than we have vertices at the end of the graph. So if it's all connected in a cycle, then we're going to have the same number of edges.
Ooh, that's interesting. Okay, so I want to use that thought. We're going to hit that one at some point, probably today. But what you're saying is that as you're growing this graph, growing this tree, you start with one vertex, and then it's plus one vertex plus one edge. So there's always an imbalance where there's one more vertex than edge. That is true. But I'm actually, we're going to use that by the end. But for this particular thing, I'm not saying that the whole graph is the cycle. There could be like other nonsense coming off of it. So I'm just saying that the graph contains this cycle. And I want to say that that's just not possible. Is there some other way to find out that that's not possible? Braden.
Well, if we consider the last vertex that is place of this cycle, we have two edges that are on that vertex that are in the cycle. But when we place the vertex, we can only draw one of those edges, not both.
Yeah. So the key is, you see, when this last vertex of the cycle got put into the cycle, well, only one of these two edges can be put in at the same time as that last vertex. Only one of the two. Okay? So here, only one of the two highlighted edges can be added right now. Remember my time is like, this is the time that I put the last vertex in. At this right now, I get to add one of those edges. Now, you see, if I stare at this, I will be able to then conclude that I can't possibly, by the end, have all of them. I see, Chris, you also wanted to say something. Do you want to finish up on that?
Well, I had a question.
Question.
So
So what you're saying is that, well, there's this cycle here that grew somehow. We're pretending that the cycle grew somehow, and it's like, well, maybe the root was like way over here. Well, then let's not consider that to be the root. At some point, everything has a path to the root. So here's the first vertex of the cycle that grew. That will be my new root. I call that the pseudo root. The only thing about this is I'm just trying to say, maybe we could make that work. Maybe we could make that work. But the problem is, I don't yet completely know that if I just simply chop off from there to the root, I won't have like more random stuff straggling off. Because you see, what Andres said I want to use, we're going to use that before the end. But what he said is just sort of, if I just stare at this thing and say, on this zone, add up the edges, add up the vertices, there's always supposed to be an imbalance. We don't yet know that super clear. But let's go to this thing, which this is like a very like hard iron way to explain this. It's like somehow there's this last vertex that got added. And there's these two edges that need to get into the cycle eventually. Here I get to add one of them, because right now I add one edge. But now the reason I never get to add any more of these edges, right? The important thing is that these two edges weren't there before. They can't have been there before because this vertex wasn't there before, right? So before, these two weren't there. And now I get to add one of them. But after, I never get to add any more edges inside the cycle, because every time I add an edge, it's like an edge to a new vertex. Did that sort of make sense? I'm like, there's a before, there's a now, and there's an after. And so only one of these two can be added right now, and neither was there before. That's the important thing. And neither was there before. And neither can be added after either, because every time I add to a new vertex. And in future, well, never again, and never again. Since always edge to new vertex. Let's just say it that way. Right, we always add an edge to a new vertex. So that's a simple way. Whenever you're trying to argue about things in graphs, you can often think about the last time something was added and try to find some contradiction. I'm just showing this because the more sophisticated you go and do these kinds of proofs, the more difficult it is just to see that something is true. And then when you can use a proof by contradiction and just focus on something, oftentimes it's useful to think of the first or the last time something was added there. So are there any questions today so far on this particular containment, which says that everything that you can get with the tree growing procedure just so happens to be connected and acyclic? So that one's the more reasonable one. The other one is weird. The other direction, we now have to do proof of the other direction. What this is it's supposed to say, hey, I have a graph. It's connected, and there's no cycles. And that's the only thing I know about it. Given connected acyclic graph. Okay, we're supposed to show that you can make it out of the tree growing procedure. Prove you can make it by growing. At first, this looks crazy. Because what do I know about my graph? I can't even draw it. If somebody just tells me, hey, you got a connected acyclic graph, I'm like, okay, what's that? I don't know, just some blob of stuff. I don't know anything. So how would you ever grow something? Well, this is interesting because it gets to some concept that we said last time. On Monday, we introduced the notion of a leaf. If you remember, a leaf was a vertex whose degree is 1. I'm going to scroll back to one of these other images. And, we had some things. This is a leaf. A leaf is any vertex which has degree 1. Now, if I'm supposed to show that I can grow, if I'm supposed to show that every graph can be grown, it turns out that the way you grow it is you kind of work in opposite. Oh, raise hand. Advait, what did you want to say?
I was thinking, could you just pick any vertex and just start growing from there?
Okay, that's a good thought. Let's try. So suppose I start with this like connected acyclic graph. Start from a vertex and then start growing from there. And hope that it works is what you mean.
If you pull some sort of like, the number of vertices is 1 more than the number of edges type thing.
Yeah. Yeah. Okay. So I can see that working. I can see that working. What you're getting to is a concept called depth first search or breadth first search, where you kind of explore. If you just got on a graph and you don't even know what it looks like, you're like, okay, I'm here on this vertex. Who's nearby? And you go and start mapping out your graph as you go. You could do it that way. Actually, that will work. I'm going to do it a different way, only because the different way is a little bit easier to explain. But you could try to do it that way. The other way I want to do it is by destroying the tree. I want to show that you can go backwards. You see, because in math, you can go in both orders. Even though it is true that in biology you grow a tree by kind of growing the tree, and in math you can say, well, if I could just like destroy the tree in reverse, then you just reverse time, and then you have found your way to grow the tree. What I'm trying to say is that it all boils down to just one statement. To do this, we'll have a lemma. The lemma says, if I have a connected acyclic graph, then it always has a leaf. Actually, I need to be more specific now. I was giving this talk to teachers about last week, and teachers are really specific. They caught me. In fact, the statement I wrote is false. I need to say finite. I forgot the word finite. So, it's just like everything we're going to do here in this class is finite graphs. And I will probably forget that word a lot. But here, since the teachers reminded me, let's add the word finite. Okay? And now that I've added the word finite, let me go into this lemma. The lemma says, suppose I have a connected acyclic graph. It's finite. Okay? So given a finite connected acyclic graph, I'm also going to say with at least two vertices. Then it has a degree 1 vertex. That means a vertex whose degree is exactly 1. Now, why did I put this thing of at least two vertices? Can anyone tell me why that's there? And Andres. Yes, because otherwise it is false. So if you had only one vertex, by the way, a one vertex graph is very boring, and it is connected because you can get from any vertex to any other vertex. There's like no other vertex, and it's acyclic. Come on, there's no cycles. So somehow that's like the dumbest graph in the world is the one vertex graph. But unfortunately, that would be a counterexample to this. In this class, you will notice I will often make mistakes where I forget to tell people I want to leave out the dumb tiny graphs and the ginormous infinite graphs. Because these two things I don't usually think about. You don't need a whole theory of graphs to understand the theory of all one vertex graphs. There's like not much else you can study. On the other hand, on the infinite side, if you like infinities, oh boy, Carnegie Mellon has some really, really advanced professors who think about all kinds of different infinities, who are working about infinite combinatorics. That one I don't understand. Then they're like, well, what if you had uncountably many vertices where the degrees are all countable? Oh no, to me it's too much. But anyway, they do good stuff. And this is out of great respect for them, that if you like all the different notions of infinities, you can have your fill with their classes. Okay, but now over here, I'm putting this thing here. You always will get a degree 1 vertex. I often like to explain, why do I care? Suppose I knew this lemma. Why would that be useful? Before we prove the lemma, let's go and show why it's useful. Now let's assume the lemma, for now, not for contradiction, but to show why we'd care. I'm one of these people who likes to know, like, what's the roadmap before I go in and try to prove some lemma. So can someone tell me, like, how you would prove the entire theorem? The theorem says, given a finite connected acyclic graph, show you can grow it somehow. And I claim that this yellow lemma is the heart of it. And I gave some hint of, like, reverse construction. Can anyone help me out with that? Ah, yes, Andrew. That's the key. It's that you will always have a connected acyclic graph. So the way I do this is I don't do like the full formalism of an induction proof. What I'll say is, continuing this proof, what you have is, all right, I start with some giant thing. This is how I think of a connected acyclic graph. It's finite, by the way. I'm just going to put that in parentheses, but it's a connected acyclic graph. Connected and acyclic. Okay, and I just drew a big rectangle because I don't know what it looks like. I haven't proven anything about its structure. But oh, the lemma tells me something. There is a vertex of degree exactly 1 somewhere. Here, thanks lemma. So lemma gave me this thing, and there's this vertex of degree 1. And now what you just said is remove it and like do it again. But the key, in order to be able to do it again, let's cut it off. Cut off this vertex. And now I have another graph. So you see, I'm drawing like a blob inside the rectangle thing because I just took off one vertex, but now you made some key observations. First of all, the thing that's left after I chop off this lonely vertex with only one edge, the rest is still connected, right? Because this guy I chopped off is not helping you connect anybody. It's just a lonely one sticking off. So chopping that off won't break the connectivity of everything else. These are important observations. So the rest is still connected. And I'll write this, I'll annotate the cutoff. Cutoff, and it won't disconnect the rest. That's like a really important point. Won't disconnect the rest. Okay, but the rest is connected, and the rest is like still acyclic. Removing stuff will never make you a cycle. You can't make cycles by taking stuff away, right? So it's connected and acyclic. Hooray! Well, if that's the case, then the rest, you can apply lemma again. And the lemma is going to give you some other vertex of degree 1. Lemma gives you this. Another vertex of degree 1. And you just keep repeating. Cut off. In this diagram, what I'm trying to emphasize is that, you know, whatever there was there, that vertex, that's still in, right? The vertex, whenever we cut off, we just cut off one vertex and the edge that's attaching it. But when I do a second cutoff, I leave the fact that there is this vertex which is still living there. It's still there. Is this making sense to people? So I keep going. Keep going. Until at the very, very end, what you've gotten is you've gotten down to here. And I guess this has two vertices. Lemma gives you one vertex here, which goes out. And then after you take it off, you have one vertex left. And then what this is this is just the tree growing procedure in reverse. Does that make sense? So if what we've done is we've found a way to start from the whole graph and keep removing these leaves all the way down until we get down to just one vertex left. Well, then just reverse time and start from that one vertex and grow the whole thing up. Does that make sense? So I call this, oftentimes in math we're trying to make constructions. Constructions are how you construct something. This is called a destruction. And you just like do the destruction and then you do the time in reverse, and that's a construction. So that's all. Construction is just time reversal of a destruction. So what this really was this was a destruction. Let me write it in a legible way. Then reverse time. And that gives you a construction. By the way, destruction is not a mathematical technical term. You won't find it in any other textbooks or anything. But that's just how this is in my head. So now I know my goal is just to find these degree 1 vertices, which are actually called leaves. In fact, even if you don't have a tree, oftentimes people will still call a degree 1 vertex a leaf. That's just quite customary. So now the whole goal is, let's prove this yellow lemma. So the goal now is to show that as long as I have some finite connected acyclic graph and it has, at least two vertices, then there's always one of these leaves. Actually, that also looks kind of strange type of statement, but at least it's one that I can get more of a handle on than saying I can grow everything. Growing is too sophisticated. But I just want one vertex with degree 1. Braden, did you raise your hand?
Yeah. Well, we know that since it's connected, every vertex is going to have degree at least 1. So there's no degree.
Okay, so I like where this is going. If you don't mind, I'm going to first rewrite the lemma statement, and then we'll have a whole space to deal with this, okay? So it just remains to prove this lemma. And the lemma says, what? Finite connected acyclic graph. Finite connected acyclic implies, I'll write it backwards E, there exists a vertex of degree exactly equal to 1. By the way, exists, there can be multiple. It's not just unique. So now it's proof time. You said something interesting. You said it's connected, so all the degrees are at least 1. You better not have a degree 0. So I'll write that as connected. Oh no, I missed something. At least 2 vertices. At least 2 vertices. Finite connected acyclic, and at least 2 vertices, because I'm about to use that. So it's like if I've got at least 2 vertices, well, I've connected and at least 2 vertices. That implies all degrees are at least 1. That's clear, because if I have a degree 0, not going to be very connected. All right, so I think what you're saying is, well, let's hear what you're saying. What did you want to do with that?
Well, now if we assume that all of the vertices have degree that's greater than or equal to, well then we can just like keep moving around all the vertices and we're going to find a cycle.
Yeah. So the idea is, like, let's assume for the sake of contradiction now, right? We know for sure all the degrees are at least 1. Assume for contradiction there's no vertex of degree 1. So no vertex of degree 1. Well, that's going to force that all the degrees are at least 2. All the degrees are at least 2. And now what you said is you can kind of move around, and that's exactly what the idea is. So far we've already used the connected, right? We've used the at least 2. It remains to use the finite and the acyclic. So somehow we need to die with the finite and the acyclic. And what happens is you say, okay, here we are. Just like start with any vertex. Pick any vertex. And then start moving. The degree is at least 2. If the degree is at least 2, I can go out of it somehow, right? And why I can go out is because the degree is at least 2. So I can go out. I'm using the word out even though this is not a directed graph. There's no arrows saying whether I go out or in, but it's just like start walking, right? And Advait, you also raised your hand. Did you want to add something?
Oh yeah, no, I was just gonna say if your graph has like n vertices, if you do this for at least like n plus 1 steps, by the pigeonhole principle, you've overlapped somewhere and you have a cycle.
Yes, so you can go out. And now the important thing is why the degree at least 2 was important is because, see the one you went to? Well, that degree is at least 2. So if I can go into it, I can go out of it also. Right? That's the important thing. So you can go out, and now you can still go out. Can still go out because the degree is still at least 2. Every time the degree is at least 2, so I just kind of keep going. Okay? Go, go, go. And now you start to get into trouble. Because this proof I call the snake proof. There's this game called Snake, right? And if you run, I don't know if people still play this game, but anyway, it was state of the art back in the day. But so you have this game called Snake, and you go around, and as you go around, eventually you crash into yourself because it's finite. So, oops, snake. That's because it's finite. We just used finite. And now the deal is if you do the oops with the snake, now I have a cycle. That's a cycle. So then that's bad. Contradicted acyclic. Contradiction. Okay. So that's actually it. It's somehow just having the fact that all my degrees are at least 2, that's really helpful because then I can just kind of keep walking and walking and walking and walking, and at some point I'm going to crash into myself. Okay, just a recap of what happened here. We now actually have a legit proof of how you can use just connected and acyclic to get that every such thing you can get from the tree growing procedure. And the proof is actually quite nice. The only thing that happens is you say, well, I just need a construction, which is a destruction with time reversed. Therefore, I just need to show there's always a way to figure out what was the thing I added at the very, very end. That's actually the motivation. If I want to reverse time, I just need to know always, is there the last thing I just added that is a lone vertex with exactly one edge coming out? Okay, that motivates the yellow lemma. And then the yellow lemma actually just boils down to go walking. And some of these proofs in graph theory at the beginning, they will be these kinds of go-walking proofs. And we'll see some more of these. Next one will come on Friday. Okay, so now we have this nice thing. Now for the rest of this class, if I say the word tree, I will be interchanging between connected acyclic graph and can be built with tree growing procedure, and we know they're the same. But we had some other things that were already brought up. There was a nice observation, which I'm already going to write down. It's a fact. Okay, fact. Well, one fact is that every tree, because we now know they're the same thing, so every tree has the number of edges equal number of vertices minus 1. Okay? And now this is why it's useful to have these two different characterizations of tree. Because if I said, all right, is it easy to prove this? Well, remember, tree means connected acyclic graph. If someone told you, hey, I have a connected acyclic graph, show the number of edges is the number of vertices minus 1, what you'll say is, well, that sounds too complicated, but I know that's the same thing as the tree growing procedure, and obviously from the tree growing procedure, that's true. Does that make sense? This is why it's useful to be able to flip between the two characterizations. So for example, the proof of this fact, there's a proof here. The reason it's a proof, by the way, is because the definition of tree was connected acyclic. It wasn't tree growing procedure. Tree implies there exists a tree growing procedure. And obviously from the tree growing procedure, this is a true fact. The result is obvious from the procedure. Okay, so that's a nice fact. And we now know that somehow if I have a tree, it always has this number of vertices and edges combination. But now something also gets kind of interesting, because it turns out that now we can start to play a little bit among these three things. We have some notion of connected acyclic. We have some notion of can we grow with a tree growing procedure. We have some notion of like vertices and edges. So now here is an interesting theorem. Every connected graph with number of edges equals vertices minus 1. I'm already getting lazy. I'll say E equals V minus 1. That's what we just wrote up there. Is acyclic, has no cycles. I'll write is acyclic. Then we are using the same words. That's a neat fact. Now, remember, connected just means that any vertex can get to any other vertex. Do I need any weird stuff like at least 2 vertices? No. I mean, I think I need finite, but I guess that's sort of clear because I'm not going to do arithmetic with infinity minus 1. So let's just take finite as like given in this class. How would you go about proving this? Chris?
So if you take an acyclic graph and then you add an edge, then if you add an edge, that must make it cyclic. And then when you do that, then it's like no longer going to be cyclic. And then if you add a cyclic graph, so the one cyclic graph and then you use one edge to break the cycle.
Okay. So this is interesting. You just used a notion here of like a maximally acyclic graph, which also is going to be interesting. So I'm just going to make a comment you said there. You said something about like start with acyclic graph, add any edge, and it suddenly has a cycle. Is that your sort of a notion? I'm just going to say, hey, here's a neat idea. This could actually be useful in making one of these proofs we're doing. A maximally acyclic graph means adding any edge makes a cycle. That's running into my head, but this is a useful concept. In fact, that's also related to everything we're doing. Okay, but I'm trying to show it's acyclic. I'm trying to show there's no cycles at all. So I'm saying that somehow I have a connected graph, and it happens to have E equals V minus 1. And now I'm supposed to show that that has no cycles. But I don't yet know that it has no cycles. There's something quite analogous to this, though, that's going to be quite useful. Anyone else have a thought? Because my given here is I'm connected, and I have the right number of edges. Braden.
Well, since we know that the number of edges is less than the number of vertices, and since connected implies that the degree of each vertex is has to be a leaf in this graph.
Mm-hmm. So, oh, okay. So you're like, it's connected, and the edges. Okay, so you see, this is where it's getting a little complicated, though, right? Because I'm like, I know a lot of connected graphs with no leaves, like complete graph, no leaves. Okay, so I'm wondering where you're getting that piece from. You're like, it's connected, and the number of edges is less than the number of vertices. How does that tell you that you definitely have a leaf?
Well, we know that the sum of all of the vertices is twice the number of edges.
Oh, that's one way.
It's going to be 2 minus 4.
Okay, that's another way. All right, so here we're making up a bunch of ideas, okay? So it is actually also true that, yes, okay. So what you also know is that somehow, or if I've connected, here I have to worry a little bit about, do I have 2 vertices or 1 vertex or something? Let's not worry about that for now, because if it only had 1 vertex, you probably can prove it. But if it's connected, implies, I'll write the parentheses, and at least 2 vertices, implies that no degree 1 vertex, vertices, okay? And you know also that the sum of the degrees is equal to twice the number of edges. That was this handshake lemma which we did last time, and you're simply saying that's less than 2 times the number of vertices. So now from that you're concluding that since there's no degree 1 vertex, no degree 0 vertices. That's what you wanted. No degree 0 vertices. And then now, like, look, if I have a bunch of vertices and the sum of all the degrees is less than 2 times it, then I better have some degree which is strictly less than 2, and it's not allowed to be 0, so it's 1. Okay? So this implies that there's a vertex with degree less than 2, and combining that with this degree, no degree 0, it implies that there's a vertex with degree 1. And you're like, then I can get a leaf. So your idea was presumably find the leaf, pull it off, and do it again. This works. So you can turn that into a proof. You can say, like, I can take this leaf, yank it off, and now the remainder is still connected, and since I took off 1 vertex and 1 edge, I conserve this condition, because once you pull it off, the edges goes down by 1, vertices goes down by 1, and it's still true. So that's okay. That's true. And what you notice is the proof is quite similar in nature to what we did earlier. It has very similar elements. Find a leaf somehow, and then pull it off. So if you see that much similarity, one question is, could we find a way to just like use the previous fact? And for that, I'm going to give an alternate proof. That's why I'm using all these colors here. An alternate proof is actually doing something very similar to what Chris was suggesting. Chris was saying, look, if I took an acyclic graph and I saturated it by like adding more edges, add, then eventually something interesting is going to happen. Every new edge is going to make a cycle. Well, now there's something else that we can do here. We can say, suppose I have a connected graph, and suppose it has cycles. Suppose I have a connected graph, suppose I have exactly this many edges, and suppose it has cycles. Well, what if I try to get rid of the cycles? So I'm showing like there's lots of different ways to do this. The way graph theory works, there are multiple different proofs. I'm just trying to show how a bunch of concepts, today is just like a whole lot of concepts that end up being very related to each other. Connectedness, acyclicness, and the number of edges being right, and then this like leaf business, okay? So here's another way. These are all like different angles that you could try to use. Another angle is, or, assume for sake of contradiction there's a cycle. Assume, for contradiction, that it's connected, the edges equals v minus 1, and there are cycles. Oh, well, if there's cycles, let's break some cycles. I don't like cycles. So as long as I see a cycle, rip out an edge. What does that do to your connectedness? It's still connected, right? Like the point is like if you were supposed to go from here to there and you were supposed to use that edge, go the other way around. Does that sort of make sense? Every time you have a cycle, if you just ripped out one edge, so what's going on here is while loop. While there exists a cycle, which might look something like this, And by the way, there's like all this other stuff. There's like other graph all around. It's just that there's a cycle inside the graph. Simply rip out an edge. If you rip out the edge, you can always, if you were supposed to use the edge to get from point A to point B, then go around the other way on the cycle. Did that make sense? And this makes sense if you just like think of any roads in the world. If you had a cycle thing, and these are two-way roads, you blow up a road and you can still go around. Don't blow up roads. Okay, so this thing, you just like tear out an edge. Okay, so while there's a cycle, remove one edge. Still connected. Now, can someone help put the piece into the puzzle? Why is this great? Suppose I just do this and like rip out edges, rip out edges, rip out edges. How does this like give me a contradiction? I see, Advait, you have your hand up.
So this decreases the number of edges by 1 and keeps the number of vertices the same. And you just do this until you hit a tree and then it's a contradiction.
Yes, the point is like, just keep destroying the edges. At some point, it's going to be acyclic. The reason is because if you got rid of all the edges, it's very much acyclic. So, but I won't get that far because I'm maintaining the connectedness, right? So as long as there's a cycle, take it away, take it away, take away one edge, take away one edge, take away one edge. Boom, the number of edges goes down, and this terminates. That's actually where it's important here. This is an algorithmic proof, so I need to say if I do and do and do, is it a finite number of steps? Okay? So what happens is you keep losing edges, but eventually stops. No, eventually you can't do it anymore. Eventually can't continue. But that's because we had finite. That's where finite was so important. We start with finite, so eventually you can't continue. And when you can't continue, there's no more cycles. So it's acyclic. That's what can't continue means. But now we just use this fact that we had. Connected acyclic graph is supposed to have E equals V minus 1. So hang on a second. You couldn't have taken anything away at all. Is that clear? Like that's the proof. You just can't take anything away at all. So acyclic, and just to let's just finish it up here on the top. Okay, so finishing it up. Finishing. What happens here is that you end with connected plus acyclic, and that implies that it is a tree. And that implies at the end E equals V minus 1. At the end. And so you better not have done anything because you started off with E equals V minus 1. So you couldn't have deleted anything. Okay. Now, the thing that Chris had said, it's quite related. Chris's idea is something about like adding stuff. Can someone give me another statement? I have this green theorem. Every connected graph with E equals V minus 1 is acyclic. Can you give me another theorem statement, which is also true, which has a proof which is sort of the dual of this in some way, using some idea that, like similar to what Chris had said? Advait.
You just say that every tree is maximally acyclic.
Oh my gosh. Okay, so there's another thing which is also true. So it's also true that every tree is maximally acyclic. Okay, that's nice. And what that means is that if I have a tree, you add any edge at all, you make a cycle. That's what this meant, right? This meant like adding any edge makes a cycle. And why? Well, because if you add the edge, it's still going to be connected. You see where this is going? We can do the same thing. The proof would be called, well, suppose not. Try adding the edge. Is it connected? Well, it's better connected. You added more stuff. Okay. Do until you're like suddenly, wait, just a second. So every tree is maximally acyclic. You add, let's do the proof, just so I don't get confused. Proof, okay. So the way this works is assume not. Assume not. And then what you have here is that you have connected, okay, and it's acyclic, and can plus one edge. And then it's still connected. It's like still connected and still acyclic. Oh no, yeah, that's the contradiction, right? And it's still acyclic. But that implies that now the vertices, so it's now a tree, right? So it's a tree, so connected and acyclic. That implies it's a tree still. And that implies that E equals V minus 1 now. But that's no good because E was V minus 1 before. So you cannot possibly have had E equals V minus 1 before, add an E, and still have E equals V minus 1 before. So that contradicts E equals V minus 1 before. Okay? And the last thing I want to leave you with is just like a really neat equivalence. Here's like a neat fact, which is I'm going to name 3 things. One of the things is connected. The second thing is acyclic. The third thing is E equals V minus 1. So the neat thing is if I look at this fact, turns out that if you have any 2, you get the third. I didn't write the fact yet. I just gave you 3 conditions. And the fact is, if any 2 are true, so is the third. So it turns out if you have connected acyclic, bang, number of edges is equal to vertices minus 1. If you are connected and edges equals V minus 1, bang, it's acyclic. And if you are acyclic, we didn't prove that other one. Acyclic and number of edges is V minus 1. Turns out it's connected. This is all related to these notions of maximally acyclic, minimally connected. And yeah, that's our whole thing about trees. So thank you, and we'll continue next time.